In the last video, we were talking about the atom and the electrons and how the movement of electrons from one atom to another caused by rubbing or by contact could create charges. And so we now have a basic understanding of how we could get charges. Let's look at a concept of what happens when you have two different charges that are nearby each other. So let's take an object here and an object here, and let's say that this object has some positive protons in it, and so does this object. But this object is going to have lots of protons and maybe only one or two electrons. So it has a positive charge. So I guess some of its electrons must have been rubbed off somehow. But the object over here, we're going to say, was rubbed against something else, and maybe it got extra electrons, and so it's going to have a negative charge. Right? Now, we haven't learned yet how we can actually measure the amount of charge, but one of the ways we can get an idea, at least, is to simply count the pluses and minuses. Now, this isn't actually the way we quantify charge in science. We have a much more accurate way of doing it, but this is a way that will help us to at least understand the idea that we're trying to get at here today. If you count this guy, you see two pluses, and you see three, nope, not three. If I could count, looks like seven minuses, which means that this guy, his overall charge will be -5. You just kind of add up those numbers. And over here, we have a guy with 4 pluses and 2 minuses. So he obviously has a charge. If you add it up, it's 2 plus. So he's a positive charge, and we're going to call that a charge of 2. Now you'll notice I put 2 plus and I put -5. In fact, we do this. This is the difference between mathematicians and chemists and physicists. Chemists like to write 2 plus. Some people write +2, but that's exactly the same thing. It doesn't really matter. So -5 or 5 minuses, you can write it either way, and it means the same thing. So don't be confused by that. In fact, I probably will do a little bit of both. Okay. So we would call these relative numbers. This is called relative charge. It just gives us an idea of the size of each one, but it's not measured very precisely in terms of the actual amount of charge. So let's look at this for a minute. If we have a -5, I'm going to erase these guys because they're confusing. If we have a -5 and a +2, then that means that there is a difference between these two, obviously, right? There's a difference between these two charges. And the difference is a difference in something we call the electric potential. The word potential sort of means like, if you have potential, it means that somebody sees that you might have the ability to do something, even if you haven't done it yet. They think, oh, you have the potential to become a great lawyer, maybe because you argue with your mother a lot, and she tells you that you can be a good lawyer because you have potential. Electric potential kind of means something like that. It kind of means that there is a sense that something could happen. Electric potential means that something could happen because of differing charges. So electric potential is what we call this difference. Sometimes we call it something else. We have a couple of names for it. We call it potential difference as well. So unfortunately, you have to just kind of get used to all these different ways of describing it. So electric potential is one way, right here, electric potential, or some people call it potential difference, or it's often referred to as a word that you'll recognize, voltage. Voltage. Voltage, in its simplest sense, is simply the result of having two different charges. Here they are, a positive and a negative charge. And if they are different, it means that there's a tendency for something to happen. And that something to happen is there's going to be a kind of a movement. Something's going to move here. Now, when you have a potential difference or a voltage, we can imagine the voltage to be kind of like sort of a force. Okay? Voltage can be thought of as the force causing charge to move. What do I mean by that? How can charge move? Well, let me show you. We've already seen that if you have an atom, right? If you have an atom, the protons are in the middle, they don't move. But the electrons are on the outside, and those electrons can move around. In fact, they're constantly moving, right? They're moving in patterns, and we kind of have a very complicated way of describing how they move. But these electrons are buzzing. If you could see an atom, you know, our models look something like this, where the electrons are just all over the place. And in fact, our latest models are so confusing that we don't even know exactly where they are. They're just somewhere in that shape. And there's weird shapes that they move in. And so it's somewhere here, and there's shapes like this. So it's very complicated. But the main thing is that the electrons are moving. And so that means that if they're moving and they want to move, well, what makes them move? Okay, so it's voltage. Voltage makes electrons move. So in our definition here, we said that voltage is the force causing charge to move. But since electrons are the only things that can move, we could also use the word electrons here. Now, I'm being a little bit general, because this is an introduction to electricity. And in the future, you may come across something that is not an electron and moves. But for the simplicity of trying to just get our heads around this idea, we're just going to pretend for now that only the electrons move. All right? In terms of atoms, anyway. Okay. So let's go back to that little picture we had. Let's go back to our picture. I think we had a guy that had 2 pluses and a guy over here with 4 pluses. Did we not? Let me just double check. We'll get the same picture. 4 and 2. Yep. And 2 and 7. So we'll give them back their electrons and their negative charge and positive charge. So this guy had 2 and this guy had 7. 1, 2, 3, 4, 5, 6, 7. Okay. This guy over here has a positive charge, and this guy has a negative charge. We already saw that. Opposite charges attract. Remember the laws of electric charge. Now, if there was suddenly an attraction between these 2 objects, but they couldn't move. Let's say we nailed them down, put a nail right through the middle, bam, bam. Now they can't move, but there's still an attraction. And so what's happening is the positive charges of this atom on the right-hand side, this guy, are pulling or attracted to the negative electrons in the other charged object. And in fact, we can kind of envision it like those electrons all being pulled like this. Like this. Here they are. And they're all like, oh, it'd be really cool if we could get over there. 6, 7. They're all sort of trying to go this way, but they can't go. Why can't they go? They can't go because the air in between, this air right here, all this air, is not a good conductor. Electrons don't like to move through the air. If they do, they have to be pushed extremely hard, and when they do, they bump into the air molecules and they disturb them so much, they get so hot that you see you see lightning, you see sparks flying. So normally electrons, unless they're really pushed very far, will not move through air because air is what we call an insulator. So you don't actually see anything happening, but those electrons still feel the pull. They still feel that pull. And the amount of pull is called the electric force. And if you think about how much the force is pulling on each electron, you get what's called the voltage. So voltage is the force on each electron. Causing it to want to move. Now, we could help the electrons a little bit here. We could take this object, like this, and the other object, like this, and there's a potential difference. There's a voltage between them because one is positive and one is negative. And those electrons, what if we took what the air is an insulator? No one wants to go through air, it's hard. But some materials let electrons pass through them very easily. We call them conductors. And a lot of metals are good conductors. So what if I take a nice copper wire and I'll stick it between these two, touching, so we'll make it this thick. There, thick copper wire. Now these electrons are so attracted that they might decide, ooh, hey, let's go, man. This is a great path. And down they go, and they would actually travel through this wire. Now, they wouldn't all travel, right? What would happen is, this would be kind of just like the two things we're touching. They would travel until it evened out. So maybe I've drawn too many there. Let me go back and just, let's fix that up. They would travel down the wire in such a way that the charges, there's supposed to be 7 of them. 1, 2, 3, 4, 5, 6, there's supposed to be 2 there. Let's fix that up, 7, right? So 1, 2, 3, 1, 2, 7, 8, 9 in total. So maybe 4 would stay here and sort of 5 over here or 4 over there. In other words, it would try to even out. Now 4 and 5 can't even out completely, but it would at least even out as much as it could. So you might see something like that. But then once they got there, they'd be like, okay, party's over. No more voltage. Because the charge difference is gone. These are both pretty close, you know, they're both, well, what would they be? This guy would be a -2, if you add the pluses and minuses, and this guy's a -1. So maybe one of these electrons might, who knows, you might be stuck bouncing back and forth somewhere in the middle. But basically, there'd be very little back and forth anymore. So those electrons only move once, and done. That's not much good to anybody, because it would happen so fast, it would all be over, and these objects would sort of get rid of their difference of charge, or at least very close to get rid of. I could have used a better example and made it even, but it doesn't really matter, as long as it's super close. So what we've learned to do is we've learned that, well, in order to keep the electrons going, you have to keep the charge difference, or the voltage. So what we've learned to do is we've learned to take a device. There's many different ways of getting voltage. So how do you get voltage? Getting voltage. Or maybe I should put creating voltage. How do we do it? How do we keep voltage going so that electrons will keep on moving? Well, one way, of course, is by rubbing things together. We saw that. Rubbing things, friction. Because friction creates charges, and opposite charges create voltage. But this is not a very good way to run things that are useful. It's kind of fun to give your friend a shock and laugh at them, or, you know, maybe it's kind of neat when you pull the clothes out of the dryer and everything is sticking together and it's all staticky. But it's not really that useful, is it? So rubbing and charging by friction is not really a very convenient way to get voltage. The other thing we can do is we can use what are called batteries. There's an interesting thing that happens with batteries. Batteries are the result of an interesting property of metals. Metals can give electrons to each other. In fact, metals are very odd. They have very strange behaviors that only metals have. And it's quite complicated, but I'm just going to write it like this. Metals can give electrons to each other. Some metals like to give them, and some metals like to take them. So if you pick the right two metals, let's say you take a metal that's a giver, and you put it with another metal that's a taker. Well, guess what? It's possible to get electrons to move from the giver to the taker. It's kind of like a chemical transfer of electrons. And so batteries are basically made of two different metals. A typical battery is round, and it has a metal on the bottom and on the outside, right here, that I've drawn, right? The outside of the container is all made of one kind of metal. And then the top is sort of another kind of metal, and there's a bump. And that bump usually has metal that goes all the way down inside the battery attached to it, like this. And then it's kind of hard to see, but right here on the edges, there's what we call insulating material. So these two metals don't actually touch. They might be separated by cardboard or paper or plastic or something that keeps them from touching. Because if they touch, that's when they'll trade. They'll give their electrons. They have to touch. In between, there's a pasty substance in here. This pasty substance is made of chemicals that allow the metals to trade their electrons through the paste. So the giver can give his electrons, and usually the post here is the giver. He's made of the giver metal, and the black part here is the taker metal. And so what can happen is electrons can move from the giver metal into the paste, and then they turn into things in the paste, but eventually then the electrons move from the paste into the metal. And if you connect a wire to the top guy, like this, and go down here, and connect it to the bottom, which is what happens when you put a battery into a device. It connects to the metal pieces, which are connected to wires. So any metal piece can be like a wire. Guess what? The electrons will travel from the red giver into the paste, just like I drew. I'll draw another one, into the paste. Then they'll go from the paste into the metal. Then they'll go from the metal into the wire, and they will travel down the wire all the way around until they come back to where they started, and they will actually make an electric circuit. Remember in grade 9. They will keep on going. Now, the drawback is, or the problem is that over time what happens is, as the electrons go into the paste from the giver metal, it dissolves or it disintegrates. So slowly this disappears. And as soon as it's gone, the battery is dead, and there's no more electrons that can be transferred, and then the current would stop. But because this takes a very long time, we can keep electrons moving through the wire for a long time, long enough to be useful, long enough to, power our Xbox controller so that we can make it to level 79 of our Halo game. Or long enough for a radio to be played for hours and hours and hours. So that's another way. And there's also many different types of batteries and kinds of batteries that work in similar ways. The principle is the same, but the shapes and the way they're designed and engineered is kind of different. But it still involves a giver and a taker, and the fact that they will let their electrons move. A third way to get voltage has nothing to do with things at all. Well, nothing to do with chemicals or metals. Or what we discovered is something really cool. If you take a magnet, right, which is a north and a south pole, and another magnet beside it with a south and a north like this, what you create is called a magnetic field in between the magnets. If you take a coil of wire and you spin it around in circles really fast, and you attach that wire somehow to another wire like this, amazingly, the combination of the magnetism and the spinning wire causes a voltage, which makes electricity flow through the wire. And this is amazing. This is the principle behind the generator. Electricity flowing through this wire is created because the voltage is created when you spin a coil of wire in a magnetic field. Now, if you were going to take more advanced physics courses, you could learn exactly how that happens. We're just going to have to take their word for it, but that's what happens. All right? So an electric generator is when you spin a coil of wire in a magnetic field. Or you spin the magnets around the coil one way or the other. You have to spin something, and it has to be magnets and coils of wire. And likewise, if you spin a coil of wire in a magnetic field and it makes electricity, you can also use electricity backwards to spin the coil. That's called an electric motor. We'll get into that a little bit later. So this would be the third way of generating voltage by what's called a generator. A generator. So these are the three ways we can get voltage, and this way we can get voltage that's useful. The first way, not so much. Friction, rubbing, it's not going to last very long, so we don't use that a whole lot. But we do have to be aware of it because it can get in the way. Sometimes the friction and rubbing that happens in factory machinery, happens on your car tires, big trucks, it can create voltage, which is a bad thing, and we want to keep it from happening. So that's not really one of the ways we use most often. However, we all are familiar with batteries, and generators are used to generate the power that's in the walls when we plug in. Down at the Sulaks, there are giant generators that are powered by the flowing water from the rapids, and that's what makes them spin. The flowing water from the rapids makes this coil of wire inside of them spin, and then they put magnets around them, and they essentially make lots and lots of electricity. Batteries make small voltages, not very much. Small differences. So in other words, they don't push electrons as hard. Generators, though, if you make big enough coils and big enough magnets and you spin them really fast, you can get very large voltages from a generator, large enough to power entire cities. Large voltage. So this means that these generators can push electrons with much greater force than the small voltages of batteries and things. All right, and so that's basically an introduction to voltage. It is caused by the difference between two charges, and it is like a force that pushes electrons. Okay? It's actually the force on every single electron. So if you say that the voltage is 12 volts, it means there are 12 newtons of force pushing on every electron. And so that's an interesting thing we should mention. We measure voltage. Let's just put voltage is measured in volts. It's easy to remember. What's confusing is we use a V to describe voltage in our formulas, and we use a V for volts for the unit. So that's a little bit weird. Like with mass, we use an M, but we measure it with kilograms, so it's different. With voltage, it's a V and a V, so it can be sometimes a little bit confusing. So we have to just make sure we understand that. All right? And so that's the basic story of voltage. In the next video, we will talk about electric current and resistance.